Welcome back to our discussion of statistics. Today we're going to talk about how to estimate proportions using a confidence interval. Sometimes we want to estimate proportions in percentages. For example, we might be interested in the proportion of registered Democrats who support Bernie Sanders as the 2020 Democratic nominee for the US president. As such, it's reasonable to assume that we're sampling from a binomial distribution. In such a case, we'll be estimating theta, the binomial parameter. Recall, if x is a random variable having a binomial distribution with parameters theta and n, then the expected value of x is equal to n times theta, and the variance of x is equal to n theta times 1 minus theta. Now, you may or may not remember that theta here is the proportion of successes. And x is equal to the number of successes in n trials. But I should be careful here when I'm referring to theta as the proportion of successes. I want to be clear, this is the true population proportion of successes. It's not to be confused with the sample proportion of successes. Whereas if we wanted to think of theta hat is the number of successes in n trials. So this would be our sample proportion. And remember, we use sample statistics like this as estimators for population parameters. So theta hat for us is our estimator for the population parameter of theta. So if n is sufficiently large, then the binomial distribution may be approximated by a normal distribution. If we create this random variable z, which is defined to be the random variable x minus its mean divided by its standard deviation, this will have approximately the standard normal distribution. In our expression for z on the previous page, we had x minus n theta divided by the square root of n theta times 1 minus theta. So as I said previously, this theta right here is our population parameter. If we want to be able to come up with a confidence interval to estimate this, what we'll have to do is substitute our sample statistic of theta hat underneath the radical in the denominator. And that would be more clear if we were going to work through the full derivation. As you may recall from our previous discussions when we initially started talking about confidence intervals, when we were talking about working with the normal distribution, we started with our bell-shaped curve, and then we chopped off an area in the middle equal to 1 minus alpha and areas of alpha over 2 in the left and right tails. And using our notation from previous in the semester, we would say that a cutoff value of z with an area in the tail of alpha over 2, we denote that with a z subscripted with an alpha over 2. So its opposite on the other side of the distribution would be the negative z alpha over 2. So our goal is to set up a probability statement that involves this expression for z, such that if z is between the minus z alpha over 2 and the positive z alpha over 2, the area in the middle, or the probability, would be equal to 1 minus alpha. So more formally, we'll apply the pivotal method. We substitute this expression for z into the expression down here that the probability that our z is between negative z alpha over 2 and positive z alpha over 2 is equal to 1 minus alpha. Then what we do is we work with the inside expression, that inequality inside the parentheses, and we manipulate it algebraically to isolate the theta. And since we only have one value of theta in this expression versus z, because we substituted in the sample statistic underneath the square root symbol, we would be able to do that algebraically, and you will be doing that as part of your next homework assignment. If we were to follow through all the steps of that derivation, it would lead us to theorem 11.6 from the Freund reading, that if x is a binomial random variable with parameters n and theta, n is large, and if theta hat equals x over n, then our confidence interval is as follows. Our lower confidence limit is our estimator theta hat minus the margin of error, which is the z alpha over 2 times the square root of theta hat times 1 minus theta hat over n. And the upper confidence limit is the theta hat plus that margin of error. So remember, this thing right here, it's called our margin of error. And we add and subtract this margin of error from our estimator to generate a confidence interval for our population parameter. And if we do so, this produces an approximate 1 minus alpha times 100% confidence interval for theta. So let's look at an example. In a poll, 1,010 US workers were asked if they ever called in sick for just a day of rest at least once per year. 202 of the people polled said yes. Assuming those 1,010 workers are a random sample of the population of all US workers, let's find a 95% confidence interval for the true population proportion of US workers who call in sick for a day of rest at least once per year. So we identify important values. The sample size is 1,010, and the number of successes for this binomial experiment, if you will, is 202. Therefore, our sample statistic, our sample proportion, is 202 divided by 1,010, and that equals 0.2. Next, we need to figure out how to work with that 95% confidence interval. So recall, we take our z distribution, because that's what we're using to construct this confidence interval. It's centered at 0. And we're chopping off area in the left and right tails so that the area in the middle is 0.95. That leaves the area for the remaining two tails to be 0.05, which we then divide in half, and 0.025 of area goes in each of the left and the right tails. So we need to find this cutoff value, which we like to call z.025, and I already have the number written here, but how might you find it? It's possible that you might end up using something like RStudio if you don't know the answer already. This is a common value for us, so it might be a number that you start to remember, but in the event that you don't and you want to use R to help you find it, your R command is the qnorm command. You'd put in the desired area of 0.025, and if we want the positive z-score, then we would type in lower dot tail equal to false. And if we do, then we end up getting 1.96. So next, we just start with our formula for the confidence interval. We have our estimator of theta hat, and we add and subtract our margin of error. And our margin of error is this z alpha over 2 times the square root of the theta hat times 1 minus theta hat all over n. And when we take the numbers that we have from up above and start plugging them into the formula, we end up getting the 0.02, which is our estimator, plus or minus our margin of error, which turns out to be 0.025. So we'd say our 95% confidence interval for the population proportion theta is 0.2 plus or minus 0.025. And we would interpret that as we're 95% confident that the proportion of US workers who call in sick for a day of rest at least once per year is between 0.175 and 0.225. Or equivalently, we could say we're 95% confident that the percentage of US workers who call in sick for a day of rest at least once per year is between 17.5% and 22.5%. So that's how we find a confidence interval for the true population proportion. Thank you.